This is lecture number 2 of chapter 2 variable regression model, the problem of estimation. In this lecture, we are going to derive the least squares estimators in simple linear regression. Here is the simple linear regression model, and beta naught and beta 1 are the unknown parameters, and we estimate them with the statistics beta naught hat and beta 1 hat. These estimators are based on sample data, and here mu is the random error term and is not itself a parameter. Recall that the least squares method chooses the parameter estimators beta naught hat and beta 1 hat such that the sum of squared residuals is minimized. Here is a scatter plot of a sample data set, and here is the least squares regression line for these data points. Although we don't have the formulas just yet, there are infinite numbers of different lines that we could draw through these points, and this is one of them, the least squares line. This line yields the predicted value of y for any given x. The residuals are the differences between observed value of y and their predicted values based on the regression line. This value of y would have a positive residual that is equal to the vertical distance from the point to the line, this value, and this value of y would have a this value of y would have a negative residual where the magnitude is equal to the vertical distance from point to that line. The sum of squared residuals is the sum of overall n sample values of the squared difference between the observed and predicted values of y. In other words, this quantity, that is summation yi minus beta 1 hat minus beta 2 hat xi square, all summations in this lecture are indexed from 1 to n because we have n values, but for this lecture I am omitting the limits of these summations. Choosing a line that minimizes the sum of squared residuals makes some sense at first, as we would like those to be small. Here the question is, how do we find the values that gives this line, this red in color, that is the regression line? We want to minimize a certain function. Now, deriving the least squares estimators of the slope and intercept in simple linear regression. We are going to take the partial derivative with respect to beta naught and beta 1, beta naught hat and beta 1 hat. We will then set those partial derivatives equal to 0, and then we will solve for beta naught hat and beta 1 hat. Make sure that we found a minimum and not a maximum, or we could check the second order condition. We are not giving in that the detail of this one, but will correspond to the minimum possible sum of squared residuals here. Taking the partial derivative with respect to beta naught. Let's start by taking the partial derivative. Partial derivative with respect to beta naught hat. First, note that the derivative of sum is the sum of the derivatives, so we can take the derivative inside the summation. Now we have got a squared term, so by the power rule 2 comes down, this 2 comes there, and the exponent disappears, and it becomes 2 minus 1 or 1. We can't forget the chain rule, and now need to multiply by the derivative of what is inside. The brackets, as it relates to the derivative, inside the brackets as it relates to the derivative, the yi and beta 1 hat xi terms do not involve beta naught hat, so those go to 0, and we're left with derivative of minus beta naught hat, and that has simply minus 1, so we multiply with minus 1. If you can see this equation here, this is the explanation of this one. Cleaning this up a bit, we can put that minus 2 out front in front of the summation here. That is minus 2 summation yi minus beta naught hat plus beta 1 hat xi. Now there comes taking the partial derivative with respect to beta 1 hat. Now with respect to beta 1 hat, again the derivative of a sum is the sum of derivatives, and again by the power rule the 2 comes out front and the exponent becomes 1, but again we can't forget the chain rule here. Once again we multiply by the derivative of what is inside the brackets here, as it relates to the derivative yi and beta naught hat do not involve beta 1 here, so those go to 0, and we are left with minus xi, this one, this term. So we need to multiply by that. Cleaning this up, we can again put the minus 2 out front, and we are left with this summation, that is minus 2 summation xi yi minus beta naught hat plus beta 1 hat xi. And this equation here is the explanation of this one, which I have already explained to you. Now setting the partial derivatives equal to 0. Now we set the partial derivatives equal to 0 here. We have two equations and two unknowns, and we are going to solve these to find out estimators beta naught hat and beta 1 hat. For that, first of all, we will get an expression for beta naught hat, and that expression will involve beta 1 hat, and we will substitute that into other equation and solve for beta 1 hat. Note that we can simplify this right away by dividing -2 as that term disappears. So you can say that cancelling out this -2 here dividing by -2 on this as that term disappears because the other side is equal to 0. Now solving for beta naught hat. Let's solve the first equation for beta naught hat. We get these terms. Note that with respect to the summation, beta naught hat and beta 1 hat are constants. In a statistical sense, they will be random variables that take on a value once we get our sample, but with respect to the summation over the sample values, they are constant, so they can come outside of the summation. These values here. The sum of beta naught hat from 1 to n turns into n times beta naught hat, and beta 1 hat comes out of the summation, and in its terms now we isolate the n beta hat naught here. We get this by dividing both sides by n. We get this. You can say that if I divide this line, this side by n, and also dividing the left hand side of equation by n also. So here n is cancelled out with n. And here we get this. The sum of y over n gives y bar, and the sum of x over n is equals to x bar. And we end up with beta hat naught equaling y bar minus beta 1 hat x bar. That does not do much good without knowing what beta 1 hat is. Now solving for beta 1 hat. Here is the partial derivative with respect to beta 1 hat. Set it to 0. And the trick here is to note that we have already solved for beta naught hat and got an expression in terms of beta 1 hat, so we can substitute that in for beta naught hat. So we are getting somewhere because we have only got one unknown in this equation. At this point, there are many ways of going about isolation of beta 1 hat. Here let's gather similar terms together, putting yi with y bar and xi with x bar, just gathering the similar terms together. So the final equation becomes that is like this one, that yi is placed with y bar and xi with x bar. Here I am going to leave yi minus y bar and xi minus x bar groups together because of the final expression. Now we can recognize that with respect to summation, beta 1 hat is a constant and can come outside of the summation like this. And moving that term to the other side, we end up with this. Now dividing through, we have an expression for beta 1 hat, which is equals to summation xi yi minus y bar over summation xi minus x bar. This is one way of expressing the formula for beta 1 hat, but we don't typically write it in this fashion. We often write it in this way. It might not be obvious, but these two numerators are equivalent and these two denominators are also equivalent. In this formula, the denominator is the sum of squared deviations of x. That's the numerator of the sample variance formula. This one, that is sum of squares of x. If we calculate the sample variance of x completely ignoring y, that's called the corrected sum of squares of x and represented with SSXX. The numerator is the sum of the products of the x and y deviations, and this is the numerator of the formula when we calculate the sample covariance of x and y. It is often referred to as the corrected sum of products and is represented by SPXY. Now let's see that those two numerators are equivalent and those two denominators are equivalent. That identity comes in very handy and some proofs in calculations. Looking at this form of the sum of products, we can multiply through the equation by the second term splitting up the first term. Now since x bar is a constant with respect to the summation, it can come outside the summation. And the sum of these deviations for any variable is always 0. You can see from here that summation yi minus y bar equals to summation yi minus ny bar equals to 0. That the sum of these deviations for any variable is always 0, but the second term becomes 0 and we are left with the sum of products equaling the sum of xi yi minus y bar. Also note that we could easily swap the roles of x and y, so it is also equal to the sum of yi xi minus x bar. So this entity comes in handy in some proofs and derivations. Similarly, the sum of squares of x can be written like this. If we split it up as before and once again realize that with respect to the summation, x bar is a constant and can be taken out front, we get this here, and once again the sum of the deviations is 0. So this second term drops out, and of course that works for y as well. Just something to keep in mind here, as that identity comes in handy for from time to time. Now, estimators of beta naught hat and beta 1 hat. Under the least squares criteria, where we choose the parameter estimates that minimize the sum of squared residuals, these are the appropriate formulas for the estimators. Here beta naught hat is equals to y bar minus beta 1 hat x bar, and beta 1 hat is equals to summation xi minus x bar yi minus y bar over summation xi minus x bar whole square.